Hello everyone, welcome to my video. Hope everyone is keeping warm and safe. In this video, we'll talk about example 2/74. This is kind of long reading, so make sure you read the question before proceed. After you read the question, there are a few highlights I would like to make. First of all, we can see that we have an initial velocity 100 feet per second. And during the first half, there is a external acceleration other than the gravity itself, 2g, in the 60 degree for the first 2 seconds of flight. What we want to find is the maximum height h achieved and the total flight time and the net horizontal displacement from point A. So this question is different than our normal projectile motion is when the only acceleration in effect is gravity. In this case is the two parts. Second part is projectile motion. First part is not a normal projectile motion. It's also projectile motion, but with an external acceleration. So when we are setting up our question, this is something you want to think about. What's the difference between the normal or conventional physics model we're working with? So given to us, in this case, what do we have? So before that, again, we want to set up the physics model here. I want you to try this. Try to draw the flight path of this firework shell. You should end up with something like this. So at the beginning, it will be flying from A to B. This is the first 2 seconds, and let's call this part 1. And then after the first 2 seconds, it will continue to fly as a projectile motion. So probably end up with somewhere here, point C, and let's call this part 2. So what do we have for part 1 versus what do we have part 2? That's what we want to set up with. For part 1, we'll have initial velocity 100 feet per second. Right, so we're given that our initial velocity is vertically up. However, the acceleration we are having, not only we're going to have a negative g as our always known condition, the gravity, and of course we are setting up the horizontal and vertical position as our positive x and y coordinates. So not only we have a negative g, we also have a 2g. Okay, I'm just using a rough direction here, 60 degrees, right, in the direction shown here. Okay, that's these two, the negative g and 2g, are the acceleration in effect in our case. Our horizontal velocity starts with 0, and the duration for the first part is 2 seconds. That's our part 1. And then for part 2, we will get a different initial velocity when we start part 2 at point B. So part 2 from B to C is projectile motion. That means we need to find the initial velocity of point B. So we want to find the initial velocity VB naught and YB naught. Okay, what's the speed? How fast is it? And where is it? Or ideally also probably x B naught. So we want to find out, once we start our projectile motion analysis, where is it? Okay, so the most important part, it seems like from A to B. Right? When there is a external acceleration other than gravity, how do we deal with this? So we'll start from A to B by setting up our XY coordinates. We want to do some quick free body diagram. Right? Not really a free body diagram because it's not the force, it's the acceleration we want to realize, what kind of acceleration we are having in the y direction and in the x direction. So let's say we have a point here. Again, we start with, always start with gravity. Okay, that's the gravity we always have. And at the same time, there is an external acceleration, 2g. Right? Don't be fooled by being called 2g. It's not gravity. It's just happened. It's 2 times 32.2 in this case in imperial unit. Right? It's a 2 times 32.2. It just happened to be that value to be 2g. So it's a value. It has nothing to do with gravity. G in this case is a number. So similar to what we did for our analysis for velocity, as I said, in projectile motion, not only you can resolve your velocity into x and y, you can also do that for displacement and acceleration. So for your acceleration, we will have, the external acceleration, this is 60 degrees. So this will be 2g cos 60 degrees. And at the same time, we'll also have a 2g sine 60 degrees. Now you can see that this is acceleration, affects the horizontal velocity, and the combination of these two will affect what's going on in the vertical direction. So we have our ax, acceleration in the x direction, 2g cos 60 degrees, 32.2 feet per second square. Acceleration in the y direction, 2g sine 60 minus g. And remember, you're working with imperial unit here, so g is 32.2. 23.57 feet per second square. Okay, this is our acceleration. Acceleration directly affects velocity. Do you know initial velocity? Yes, we do. We have initial velocity, so we can do the calculation. Vx and Vy. Using our constant acceleration formula, 0 plus ax times time, 100 times a plus ay times time. Okay, remember, we're still working with constant acceleration for the first 2 seconds from A to B. Okay, from A to B, constant acceleration. Subbing all the numbers. (100) plus 23.57 times 2. 147.14 feet per second. Okay, so that's the velocity of where? Remember, we start with a vertical velocity of 100 feet per second. Now, where is these two velocity? That's the velocity at point B, your Vx of point B, and Vy. Sorry, Vx of point B and Vy of point B. Okay, we dealt with acceleration, velocity. We also need to know where is it. So that's displacement. I need a bit more space here. X and Y. Displacement. X naught, Vx naught time 1/2 ax t squared. Remember, t is 2 seconds. Just in case you're wondering. 2 seconds. It's the same here. 2 seconds, 2 seconds. For y, same thing. Vy naught t 1/2 ay t squared. Okay. I'll put all the number here so you know what's going on here. First of all, we start from the origin. 0, 0, 0. Okay. We start from the origin and we don't have any horizontal velocity in the x direction. 0.5 times 32.2 times 4. Okay, you'll notice it happened to be the same value, okay, but they're in different units. That's why keeping your units is a good choice. It's always a good practice. 100 times 2, Vy naught times t, plus 1/2 times ay, 23.57 times 4. Okay, 2 squared. The 2 second square is 4. 247.14 feet. Okay, this is what we find out is velocity horizontally, velocity vertically, horizontal displacement, and vertical displacement. Okay, this is what we have so far. And all these, of them, are happening at point B. Right, so all these conditions becomes the initial condition at point B, because in part 2, from B to C is projectile motion. For projectile motion, we need initial conditions. Well, we need to know the initial velocity, we need to know the initial displacement. So all these now becomes the initial condition for point B that we can carry forward to solve for part 2. Now, part 2, as we analyzed, is projectile motion. So projectile motion, we just got from the previous part 1, we start with initial velocity, 64.4. Horizontally, vertical initial velocity. It was already in x and y direction. We don't need to combine them now. Okay, we'll just keep them as separate x and y. 147.14 feet per second. That's velocity, and our starting position x naught and y naught at point B, 64.4 feet, and 247.14 feet. Okay, these are our initial conditions for our projectile motion at point B, starting at point B. Okay, all these values we calculated from part 1 now becomes our initial condition for part 2. The question is asking when or where do we reach the maximum point? So I call this M. The condition for maximum point in a projectile motion, you should recall that is when your vertical velocity becomes 0. Right? If your vertical velocity is not 0, you're still going up. So the maximum point is defined by when you reach your vertical velocity 0. So we can start with that. At point M, or the peak, your Vy equals 0. So that gives your Vy naught minus GT And subbing out the numbers here, we start with 147.14 minus, in the second part, there's no more 2g extra acceleration. The only acceleration in the second part is gravity. Okay, remember, in second part is only projectile motion, the normal projectile motion. So the only gravity in the vertical direction is 32.2, and there's no acceleration in the horizontal direction. So you can find out time, 4.56 seconds. So it takes 4.56 seconds from B to M. Just remind you, this is from B to M. And how high is it? Y BM. The displacement from B to M will take Y naught, initial velocity, the T, B to M, minus 1/2 G T squared. Remember, time is from B to M. Okay, subbing all the numbers here. I may need a little more space here. Okay, 147.14, 4.56 minus 1/2 gravity minus 4.56 squared. I'll get my displacement, y from B to M, vertically, 583.14 feet. Okay, with that, finally, we'll calculate where is our ending point C. Okay, our ending point C, what do we know about ending point C? Think about that. Similar to what we know about the maximum point M, we know the velocity y has to be 0. And remember, for point C, you're coming back to the ground. That means, vertically speaking, in the vertical direction, you're coming back with 0 vertical displacement. Make sense? So that means when I'm calculating YC, that is YM plus velocity MT minus 1/2 GT squared. And where I know this will be 0. I know my displacement at YM, and my YM in the vertical direction, I should say, I'll just make a note here. This is vertical velocity. Vertical velocity at maximum point is 0. So what do we have in this formula is giving us 0 equals to 583.14 minus 1/2 GT from M to C squared. See, we are finding out how long does it take to fall from M to C, while knowing this is 0, this is 0. The only term we have is these two, and has an unknown term t. That's what we want to find out. So given that, subbing everything, you should get the time flying from M to C is 6.02 seconds. So finally, you'll combine everything here. The x displacement from B to C is your Vx naught t. Since we start from part B, is there any changes to our horizontal velocity? No, because there is no acceleration in the horizontal direction. So our horizontal velocity for this entire time while we're working here remain the same. So our horizontal displacement, as long as we know how far or how long does it fly, we can calculate the displacement. Right? It's a constant velocity times time give you the displacement. 64.4 comes from here, multiply the time. Remember, the time is from B to C. So you need the time here and time here, which is this plus this. B to M, then M to C. Just remember there are multiple parts going on here. $681.35 feet. That's our total displacement from B to C. But remember, the question is asking the total horizontal displacement, the total flying time, and the maximum height that this firework shell can reach. Although we already have that number already, it should be 583.14. Okay, so I may have a typo here. There should be 3.2. Okay, so put everything together here. We've got horizontal displacement BC, 681.35. Horizontal displacement AB, we got from first part, 64.4. So that gives you the total horizontal displacement, XAB plus XBC, is 745.75 feet. Our first answer. Total horizontal displacement. Okay, and the total time will be the time from the first part, 2 seconds, plus the time from B to M, plus the time from M to C. Adding all them together, 12.58 seconds. Our second answer. And third one, the Y maximum, we've got that already. You just copy that, 32 feet. Okay, the 3 answers we're looking for. Thank you for watching. I'll see you next time.